start with this section, what I want to do is walk you through how to calculate the area, the surface area of a frustum, which is essentially like a piece of a cone without the top portion of it. So your book goes through stuff here, and I'm going to go through the same thing. But what I want to do is, before we calculate this, I want to show you that this guy right here is true. Okay, so let me walk you through that. Okay, so let's say, for example, that we wanted to find the surface area of this particular cone. Okay, so here's what I'm going to do. Let me walk you through the justification for why this is the surface area. Let's say we had a cone. Okay, I'm going to draw you guys the cone here. There's the height of the cone. Here's the radius value. It's an altitude, right? Okay, so this we'll call H, this we'll call R, and this I'll call L for the slant height, right? This is the length coming down, like if you're going to sit on top of the cone and slide down. Okay, that's that length right there. Okay, now what I want to do is I want to find a formula using H, R, and L. Okay, however, I need to put these guys together to find the surface area of this guy. So if you were to take a cone, you were to cut it, like cut it up along one of these sides, and they'll say there's nothing inside. Like think about it like an ice cream cone or something. You cut it, okay? What you end up with is a larger circle, okay, with a piece cut out of it. Right? Anyone that's ever made a cone out of a flat piece of paper, you draw a circle, you cut a piece out, you cut this piece out right here, okay, and then you take and you remove that piece, right? We remove this, and then we put these two pieces together here, and we get our cone. Okay, so let's look at this. When we flatten this cone back out, because this, by the way, this yellow area in here, that is the surface area that we're looking for, right? That is this outside surface area here, not including the bottom of the three-dimensional thing, okay? Okay, so we've got that. So what do we want to find here? Well, I need to come up with a formula for this guy on the inside. I'm going to call it SA for surface area. Now, what do I know? Well, I know that this circle right here has a radius of L because it has this slant height. So I know that this guy right here is a length of L. Of course, this guy over here is also a length of L. Now, what else do I know? Well, I know that let's see here. What can I share that now? Well, I know that the area of this whole blue thing, so that includes the blue plus the yellow, the area of this larger circle. Okay, so the area of the larger circle is going to be equal to pi times its radius, which is L squared, like that. Now I don't know the area of the smaller section here. That's what I'm trying to find. So the other area, I'll put it in yellow. I'm trying to find, we'll call that the surface area. Okay. But what I'm going to do is I'm going to compare it to the following. I'm going to compare it to the ratios of these lengths. So this length compared to this whole length. Okay. So what I'm going to do is I'm going to take the proportion of this length here in green versus the total length in blue. Okay, so what we have is the circumference in green. Okay, now this length around here, you may say, well, we don't know that. Well, we do, because this length around here is the same as this length in here. Well, what is that length? Well, that length is the radius times 2 pi. So 2 pi times the small r, this length right here. Okay, now the total circumference of the blue Well, that's equal to 2 pi times L. Now here's the deal. The ratio of these guys is equal to the ratio of these guys, right? Now these two are the two that match up, and these two are the two that match up. So I just have to make sure that they match up in my formula. So surface area over pi L squared should be equal to, so the smaller one with the smaller one, 2 pi r over 2 pi L. So what cancels here now? Well, the 2 pi's are gone. So what I'm left with is that the surface area is equal to r times pi times L squared over L. Now L's a positive number here. L's non-zero, right? Okay. So we can say that the surface area is equal to pi times r times L. Okay. Or another way of saying that is that surface area is equal to pi times r. Now, because I made a right angle here, L is equal to the square root of these two guys. So we'll go h squared plus r squared, just like that. So if you go to your book, I'm pretty sure they've got, they've got r squared and h squared, r, and pi. And if we go back, r squared, h squared, r, and pi. So look, that's where they're coming up with that formula for the surface area. Okay. Now what we need to do is we need to calculate a section of the cone. So what we're going to do is we're going to take an arbitrary cone, like this, and then of course it comes down like this, and looks something like that. And now let's say that this cone, okay, has I don't know, a height length out to B, okay, and it has some, I'm going to go out here just a little bit, just some length A. I'm trying to set this up like your book has got it down in here. I'll show you. Okay, so we're setting this guy up right here. Okay, now what they said is, okay, look, let's say that this edge of the cone was given by an equation. Okay, let's say it was given by f of x is equal to c times x, where c is clearly some constant. So this is linear, right? This line cuts through the origin. Okay, so we've simplified things real well here. Okay, so now what do we have? Well, this length out here is a. This height length right here is f at a, which is c times a. Okay, so I get this right in here. Now let's get this guy over here as well. Okay, so this guy right here is f at b, which is c times b, like that. Now what I want to do, there's a smaller cone in here. What I want to do is I want to cut the top cone off, and I want to come up with the formula for this inner cone surface area right here. Okay, and that's essentially this right here. I'm going to come up with a formula for this. So what we're going to do is we're going to take the surface area of the whole thing and subtract off the surface area of the top, and we'll get the surface area of this Trussman. Okay, which by the way is misspelled here, but is cool everywhere else, it looks like. I didn't see any other misspellings. Okay, so what are we going to do? Well, let's find the surface areas. So the surface area of the larger one, using this idea, so the surface area all the way out to B, okay, is going to be equal to pi times the radius. Now the radius here is CB times the square root of h, okay, which is the height, so that's b, so b squared, plus the radius squared again. And so the radius we know is CB, so plus CB squared. Now this takes a little while, guys. When you're reading through the book, you can't just, so let me be very clear on this. You can't just look at this and be like, oh yeah, okay, that makes sense, like I read it. No, you gotta sit down and play with it like this, okay? And work things out yourself. If you're not sitting here writing these things down by yourself and you're just like reading the book, it just doesn't help you, okay? So what do we have here? Let's see if we can simplify this a little bit. I think I can get rid of a b in here, so watch. I've got pi c times b times the square root of b squared times a quantity 1 plus c squared. You see I pulled the b squared out like that. Now b is a positive number, so we take the square root of b squared. It's equal to the absolute value of b, but b here is positive, so no big deal. We'll just make this equal to then b. Okay, so we're good there. And so this will be pi times c. Now when I pull the b out, because really guys what I'm writing here is this. Let me give you your middle step here. Okay, so this gives me this. Okay, that's the surface area of the big thing. Now, the surface area of the top cone, that's going to be pi times. Now the radius is going to be c times a. Okay, times the square root of h squared, which is a, so a squared, plus c times a squared. Now, if you want, pause the video, see if you can work down to this, but this is going to give me pi times c times a squared times the square root of 1 plus c squared. So the surface area of b minus the surface area of a is going to be equal to the following. It's going to be equal to pi cb squared square root of 1 plus c squared minus pi ca squared times square root of 1 plus c squared. So this is going to be, if I factor out, this will be pi c square root of 1 plus c squared times b squared minus a squared, which is pi times c. I'm going to move some stuff around. I don't like this guy in the back. So this would be b minus a, b plus a, times the square root of 1 plus c squared. So let's go back and look. We've gotten down now. Whoops, way too far. Okay, it looks like we've gotten down to right here. Okay, now what we're going to do is we're going to do some substituting in here. And so if you notice, okay, if I multiply, okay, so if I go back here and if I multiply, if I break this guy down and I multiply c into the b, now so these are kind of tricks. Now if you're saying, well, I would never have thought of doing that on my own, yeah, well, you know, it takes a lot of playing around so you get it to look like what you want it to look like, so don't feel bad. This is going to be pi times cb, okay, plus ca, still multiplied by b minus a, like that. So I took this c and I multiplied it into these two, and then I get this. Okay. Now, why are we doing this? Well, because cb is f at b. Okay, and ca is f at a. Okay, and so let's see here if they do any other simplifications here. This thing looks like right here, okay, I've got the b minus a times this. This right here is the length L. Okay, now how do I know that? Well, this is going to be b minus a, okay, is this length right here, and then the square root of c squared plus 1, okay, give me a second. Okay, I'm actually going to have to draw this out for you so that you can see it here. If I want, let's say I wanted, this is the length of this piece. We'll call it L. Okay, that's the length there. Now if I take that and I divide it, this way, and this way. What I want you to notice is that this length right here is CB minus CA. Okay, this length coming across is, this length is B minus A. So altogether, L is equal to the square root of CB minus CA squared plus B minus A squared, like that. Okay, now what I can do here is I can factor out a C squared, so I get C squared times B minus A squared plus B minus A squared. And I can factor out that B minus A squared, and I get C squared plus 1. Okay, so this is B minus A, because B minus A is the positive, so it's the absolute value, but B is larger than A, so okay, I don't have to put absolute values around that. And this is 1 plus C squared, or C squared plus 1. So what they're saying is that this piece right here, what's left over, is equal to L, this length up here. So this right here, guys, this is our formula for the volume, excuse me, the surface area, okay, the surface area of this frostum. Okay. Now what I'm going to do here is let me explain how we're going to use that in the next piece of this. Okay, so here's how we're going to use this. What I've got here is a curve, a random curve. Okay. What I want to know is what is the surface area of this curve, okay, as I revolve it. So if I go back up here, if I take our curve and I revolve it around the axis, I don't care so much about what's in there. I just want to know how much surface area is on this, right? Okay, so that's what we're looking at here. By the way, this is just a fun animation to play around with. Okay, so we're down here again, and we're trying to find the surface area. So what we're going to do is we're going to take a chunk of it, and we're going to revolve that like this. And then what we're going to do is we're going to add up all of these guys. Okay. I'm going to add up all these guys along here, and that'll give us, if I take each one of these narrow sections, see how they're super thin there? But they actually have no width. But I can find the amount of area on its surface. Okay, so we're going to get our whole object right in there. Okay, so there it is. Again, we're going to come along and we're going to get all these guys in here. So how are we going to do that? Well, again, what I'm going to do is I'm going to rotate that guy, okay, around, just like that. Now what I need to do is I need to come up with the formula for this surface area. Well, we already have a formula for the surface area. So the surface area is given by taking pi multiplied by the function here, excuse me, so this height and this height right here, that's this piece right here, and then multiplying it by L, the length of this. Well, what is the length of this? Well, that's not too hard to find. Okay, this length is equal to this guy squared plus this guy squared, square root of it, right there. Okay, so what I'm doing is I'm applying the formula that we just had, this formula from right here, and I'm inserting, for this guy right here, I'm inserting, let's go back, this right here, which is this. So now what we're going to do, once we have that inserted, is we're going to add up all of the different these different guys. Okay, so we're going to add up all of these, right? So that's what this means. We're going to add them all up. Now, the mean value theorem, okay, tells us that at some point on the interval, okay, if I go back here a little bit, at some point on this interval, there exists some guy, maybe right here, such that if you go up to here, it has the same slope as this guy does, right? Okay. So again, we're going to apply that same trick as we did last time. What we're going to do is we're going to say, okay, at some point on that interval, the delta yk divided by the delta x, okay, that guy is going to be equal to the slope. And so we know that we can go ahead and we can insert it into there. So again, if you're confused on this, go back and watch the video on the arc length, or the length along a curve. Okay, so we get this. Okay, and so now this piece right here, well, as n goes to infinity, f at xk is going to be the same thing as f at xk minus 1. What that means is that it means that this point and this point, as we increase n, become closer and closer together. In fact, at some point, they become the same guy, right? Okay. So at some point, these two guys are equal to the same guy, which means that I've got two of them right here. Okay? So I got two of these guys, the pi still, and then I got this guy. Now, this is now our Riemann sum, so as we go ahead and we add up, we let n go to infinity, we end up with the integral of now what's varying. Well, x is the guy that's varying, our change in x, so it goes from a to b, right? It goes from here to here. Okay, and so that's where this formula right here comes from. Okay, so what I'm going to do is stop this video, let you kind of digest that, and go on to a sample problem or two.